A6. So A6, we're about halfway through the problems and stuff like that. This is an adiabatic reversible expansion, right? We're going from 2.5 to 20 liters. And so, there's a few things that we will know right off the bat, right? And there's certain things that we can easily figure out. So we're talking about argon gas, right? So that's going to tell us, right, that it's, going to be an ideal gas in this case, right? It's a noble gas. It's really small, right? It's monoatomic. And so in this case right here, right, we have our initial pressure is equal to 1.00 atmospheres. We have an initial temperature of 25 degrees Celsius, which comes out to being 298 Kelvin, right, if we were to convert it. And then we have an initial volume of 2.5 liters and a final volume of 20 liters in this case right here. So the first thing that it's asking is to calculate what the final temperature is and what the final pressure is in this case. So one thing that's really important to think about, right, is that in an adiabatic expansion, right, in terms of calculating what the new pressures and volumes are, right, it's not going to just simply be a scenario where you can easily do it, because there's you have the relationship of P1 V1 the power of gamma is going to be equal to P2 V2 power of gamma in those cases, right? Because we don't know what the final pressure is, and it's not going to just simply be an easy relationship, right, where it's P1 V1, right? Because it's an adiabatic change that's happening. And so the definition of gamma, right, is equal to Cp over Cv in this case. And I didn't give you specifically in this problem, right, what Cp or Cv are, but you can calculate what they are, because we know that we're working with, a monatomic ideal gas in this case. And so we know that, Cv, the definition of Cv for a monatomic ideal gas is 3/2 R, right? And R is the ideal gas constant. And we know that Cp is equal to Cv plus R, which then tells us, right, that what that's going to be equal to is 5/2 R in this scenario. Now, what we can then easily do right now is then calculate what gamma is, because if we take those values, right, so we have 5/2 R divided by 3/2 R, right? The R's cancel, the 2's cancel, and so gamma is just simply equal to 5/3 in these scenarios. So, we can just easily use that right there. And so now, right, to calculate what the pressure is, right, we know that the equation is, P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. We know what the initial pressure is, right? We know what the initial volume is. We know what the final volume is. We just don't know what the final pressure is. So then that means that if we rearrange that equation, right, we have P2 is equal to P1 V1 to the power of gamma over P2 to the power of gamma. So if we plug in all the values that we have, right, so pressure initial is 1.00 atmospheres times V1, right, which is 2.5 liters to the power of gamma, right, which is 5/3 in this case. Divide that by P2, which is 20 liters to the power of 5/3. We can take all of that, plug it into our calculator, and then what we get is 1 times 2.5 to the power of 5/3 divided by 20 to the power of 5/3. And so what I got is 0.03125 atmospheres in this case. Right, so that's what P2 is. So that's the final pressure that we're ending up with in this scenario. The next thing, right, that we can do is calculate what the final temperature is. So you can go through the process, right, of using PV equals nRT, because now we know what the final pressure is, what the final volume is, but you would have to calculate first, right, what the initial amount of moles and everything like that is as well, which makes the most sense to do, actually, thinking about it right now, just because you're going to need those for the equation for reversible work in delta E. In these scenarios. So let's calculate what the number of moles are. So the number of moles is going to be equal to PV over RT, right? So we have, and we can just use the initial pressures, right? Because the number of moles shouldn't change. So the initial pressure rate is 0.00 atmospheres, right? The initial volume is 2.5 liters. Divide that by R, right? So in this case, we're going to use the R that would cancel out all of those units. So that's going to be the 0.08206 liters atmospheres over Kelvin moles times temperature, which is 298 Kelvin. And so what you get in that scenario is 1 times 2.5 divided by 0.08206 times 298 Kelvin. So I got 0.1022 moles, right? Because Kelvins cancels, atmospheres cancels, liters cancels, and then the moles end up on top, right? So that's how many moles we have. And so we can then just simply, use that information to calculate what the final temperature is, right? So there's two approaches to it, right? So we can just use the approach that I'm going to do now, right? Where I'm just going to simply use, right, T final is equal to P final V final over NR. The other equation that you can use, right, is that the relationship is T1 V1 to the power of gamma minus 1 is equal to T2 V2 gamma minus 1. In those cases, right? So you can use either one. They should give you the exact same values, right? It's probably just gonna be slightly different depending on the amount of error that gets introduced, but that's fine. And so, yep. So going in, right? So the final pressure that we have is this guy right here, right? So 0.03125 atmospheres times V final, right, which is 20 liters, divided by the number of moles, which is 0.1022 moles, times R, which is going to be 0.08206 liters atmospheres over Kelvin moles, right? Liters cancels, atmospheres cancels, moles cancels, Kelvin goes up top. So we take all of that. So we have 0.03125 times 20 divided by 0.1022 times 0.08206. And what I got was 74.5 Kelvin, right? Which should match what I have on the key, right? 74.7. Yeah, close enough. 0.0313 atmospheres. Yep, close enough. So, right, they're all pretty much the same, right? So that's how you calculate, right, the pressure and the volume in these scenarios. Now, for the work reversible and the delta E, right, we know that Q for an adiabatic process, right, Q is equal to 0. And so that means then that delta E is equal to work reversible in this case. And we know then, right, that delta E is simply equal to NCV delta T, right? We know the number of moles. We know CV, right? Because we're assuming that this is simply a monoatomic ideal gas. So that's going to be 3/2 R. And we know delta T now, right? Because we know the final temperature, we know the initial temperature. So we can just plug in all of those values. So what we get is that delta E is equal to the number of moles, right? So that's going to be 0.1022 moles times CV, right? So the CV is going to be equal to 3/2 R. So that's 3/2. And then R, right? The important thing to use here, right, is the R that has the joules, right? Because delta E and work and all those things should all be in units of energy. So that should be 8.314 joules per Kelvin mole times delta T, right? And so delta T in this case right here is going to be 74.5 Kelvin minus 298 Kelvin, right? And so moles cancel, right? Kelvins cancel. And so we should only end up with joules. And so in this case right here, what we have is 0.1022 times 3/2 times 8.314 times 74.5 minus 298. And so what I get is negative 284.9 joules, which matches pretty much what I have right here, right? So I have negative 284 joules on the key, right? And so that's what work is going to be equal to. That's what delta E is going to be equal to, right? They're going to be exactly the same. And that's how you calculate those values that we have in problem A6.